Welcome to another lecture of robot mapping. Today we're going to see the first algorithm for SLAM. So the first solution, one of the first also proposed in literature, and probably the simplest one to implement, let's say, which is based on the extended Kalman filter. So last week we've seen the whole framework of the Kalman filter and the extended Kalman filter, and now we're going to see how to implement it for SLAM. So again, a bit of recap. So this is an important problem because you have this loop of mapping and localization, and normally if you know one, you can easily retrieve the other variable, but in our case we are trying to retrieve them at the same time, so we will always rely on some previous estimate of one of the two quantities to get a new estimate of the other, and so on. To get back again formally, for the one who forgot it, we have controls, which are this U, and it's a sequence of different controls over time. You can imagine this is something that is applied to the robot, and the robot moves over time. We have some observations, which we call normally with Z, and according to which sensor we are using and which kind of map representation we are using, they will be different. But in general, the sequence of or the level of abstraction will be the same. We want to have a map of the environment, and again, this depends on how we represent it. And we want to estimate the path of the robot, or in some special case of online SLAM, we want to estimate just the last pose of the robot. Okay? That's a quick recap. We have seen different paradigms of filtering, these two. This is the first approach, which is based on Kalman filter, where you have Gaussian noise and linearized models for the motion and for the observation. We go then on particle filter, that will be later on in the class, where we relax the assumption of linearizing the motion and to have Gaussian noise. We can consider several different type of noise information and also several different type of linearized, non-linearized models, or non-linear model. However, we might lose in efficiency because we do not have a parameterized distribution, but we have what's called a non-parametric representation. And then we'll see towards the end of the lecture, which is graph-based model, which is the new state-of-the-art on SLAM. Today we go in this. I'm going to explain the standard extended Kalman filter. Next week we're going to see some extensions on the Kalman filter that have been developed over the time to deal with some of the shortcomings of the standard approach, but today we'll just focus on the classic parameterization. So Kalman filter is again an instantiation of the base filter, where we have that our belief distribution is represented with the normal distribution. So we just care about the two sufficient statistics of the normal distribution, which is the mean and the variance, or covariance if you are in multi-dimension. And we have our motion model is a nonlinear model, but affected by again, Gaussian noise, and we are considering a linearization, so a first order approximation of this model for the extended Kalman filter. For the correction, again, we will have a nonlinear observation model and affected by Gaussian noise, and we will consider an approximation of this on the first order. So by considering the first order approximation, basically this one becomes linear, this one becomes linear, and we are again into the nice framework of the Kalman filter, where we can update our statistics of the distribution, so mean and covariance, using the Kalman filter formulas. The Kalman filter is something that addresses the online SLAM problem. So we are only interested in knowing the last pose of the robots and the whole map. We are not interested in estimating the previous poses. And actually what we do during the recursive filtering, we will marginalize them out, and we do it by this operator here. So this is what we with this operation, we take all the information of the previous poses into the current one into account, and then we update the current one. Okay? So the Kalman filter, as I said, is probably one of the easiest to implement. If you want to implement it, you just need to have this. So these are in Octave MATLAB 6 lines of code, 5 lines of code, plus few lines on implementing this and implementing this. Okay, so that's what you need to do. And today we are going to go on each of these lines and show how these abstract symbols which are here actually becomes real from the data that we get from the robot. Okay, so any questions so far? No. Okay, so the first thing to consider is what is the state. No? We have seen that a Kalman filter takes a state over time and estimate some statistics on that. Since we're doing SLAM, the first thing that we need to care is that we have a part which is the pose of the robot, and we have a part which is the map of the environment. The Kalman filter in SLAM has been applied to one main map representation, which is what's called the landmark map. So the idea here, you have a set of locations in the world, which are called landmarks, and you only estimate the position of these landmarks with respect to the world frame. So a landmark can be, for instance, a tree, if you are in a forest, a trunk of a tree, or if you are at sea, it can be different stars. It's basically something that is a point-wise information of the environment that you can reliably extract from your sensor data. Okay, so that's the abstraction of the landmark. In general, if you are indoor, you can imagine this will be like the corners of the walls or some kind of pillars sticking out and so on. Okay, that's just the abstract formulation. So basically, the full pose, the full state that you are trying to estimate is for a 2D case, x, y, and theta of the robot pose, and then the x and y coordinate of each landmark. In case we go in 3D, this will be extended with x, y, and z, so the height of the robot, plus the three angles that define the orientation in the space. And for each landmark, we will then have x, y, and z. So the landmark normally do not have any orientation. They're just fixed point in the world. Another extension, which is also what you will see in the book, is to add some additional information to the landmarks, which is called signature, or like somehow a shape or appearance information. That can be a set of numbers that just tells you, I don't know, for instance, the color, if a landmark might have a color, or anything that can help you to identify or to model some aspects of the landmarks besides the position. In principle, it's the same approach. You just need to then define how this appearance can change over time and how this appearance can be observed from the sensor. For simplicity here, we just omit that, and you can look at the book. There is, I think, one simple ladder or one additional elements in the probabilistic robotics, which is the signature. I think it's a 1D variable, but in principle, you can generalize to whatever you want. Okay. Other assumption, at the beginning we assume that we have known correspondences, so whenever you observe something in the robot point of view from the sensor, we know exactly to which landmark it belongs. We'll see later on how this can be relaxed and also dealing with problem of what's called data association. So getting one observation and deciding to which landmark it belongs. And you will see that if we have some signature or some other appearance information, this gets a bit easier. Okay, so how does it work in practice? The first thing is the state. Then we see how this looks like if you have both parameters. So the state vector here, which is our mean for the distribution, which again is the same thing you've seen before, just act as a vector. And that's the mean of our multivariate Gaussian. And then we have a covariance matrix. And the covariance matrix has the usual structure. On top here, there is the covariance of the pose. Here is the covariance of the map part. And these two green blocks are the correlation between the robot pose and the landmarks. In principle, you can also go more into fine grain and say this is the variance of the x coordinate, the variance of the y, the variance of the theta, and all the correlation between x and theta. But the idea of decomposing it in these four parts is that during prediction, you will basically are only interested in the robot pose and how this changes with the map, but you're not touching the map. And during the observation, you're actually measuring something here and here, so you're touching the whole metric structure. This is just because different measurements are relates to different parts of the state. Motion only relates here, normally, and the full observation relates to the whole space. That's why we divide it in this macro block. You can even simplify them a bit further, so compactly. You say there is the pose, and then each individual landmarks, like this. Or you can even go further down, where you say, I just have a state, so the pose of the robot, and the map, and I can consider the different blocks in this way. This is just a way of compactly writing block structured matrices. This one will be a 3 by 3 matrix. This will be a 2n times 2n, where n is the number of landmarks. And this will be something which is 2n by 3, and this will be 3 by 2n. No? So that's just how these matrices are structured and sized. Okay? So that's just to make things simpler to write down if you have to write some equations. So if we get back now to the Kalman filter, we have a cycle which is made by these 5 points, which resembles also the same 5 lines of code that you've seen before. The first thing that we do is we predict the state. So we are at a certain point, we get some motion command, and we predict the state after the motion. We do a prediction of the measurement, so we know how a measurement from the state space should be seen. Then we take the real measurement, we compare those two, so we do some data association and merging update of the state, and then we do the final update. There is a last step which is somehow included in these two, is when you observe a landmark which is not yet in your state space, so then you also have a map update step. Okay, but this can be, you will see later on how this is done together in the whole framework. Okay, so in the first step, the only thing we are interested is in the motion of the robot. That's how our motion model works. So assuming we are here with a certain uncertainty, we perform a motion, we update the mean of the robot, so this part here on the state vector, and then we update also the covariance and the cross correlation. And that then gives us a more uncertain pose, because while we move, we also accumulate uncertainty over time. And the motion will decide how this thing is rotated, and what will happen is also will modify somehow. You don't see it directly here because this will stay the same. These ellipses here are just drawn by the diagonal elements of this matrix. They're what's called the marginal covariance of the landmarks. But what will change is these internal relations here. So the relation between this state, so this ellipse, and this ellipse will change. This means if we update these landmarks, the update on the pose will depend on this part of the matrix there. Okay? The second thing that we do is measurement prediction. So we do not touch at all the state or the covariance matrix, but we just use the information contained in here to get this uncertainty there. And basically what we do is we have a certain function that predicts the measurement. We take the value of this function with respect to the mean, and this gives us the location of this landmark. And then we propagate the uncertainty of the covariance matrix through this function to get the uncertainty of the predicted measurements. We'll see later on how it works when we have specific sensor measurement, sensor model. Yes? The matrix is not changing. This is something which is somehow external. This you can see as a function. No? So you basically have that your predicted measurement, let's call it Z, is equal a certain, let's do the linear thing. So it's, as we see before, is hx, right? That's how we predict our measurement. We have our linear measurement function and our state. And this will not change x, but will just create like a new variable, which is our prediction. Okay? And this has then a mean of z, which is equal to h mean, and this also has a covariance of our observation that it's equal to h sigma h transpose. Okay? So that's how we propagate the measurement with respect to this random variable here. We have linear function, random variable, this is again a random variable, and we propagate it in this way. Okay, so that's what's called linear error propagation. This propagates the uncertainty in a linear way, and this propagates the mean in a linear way. Okay, and that's what's going to happen here. So these matrices are not touched; they're just used as input for the prediction. We then get a measurement, and this just comes from your sensor, so you don't have anything to do. It will be an input to the Kalman filter in this case. Then you basically consider the association, so you associate your measurement with your prediction, you compute the error, so the difference between the prediction and the real measurement, and by using this you feed it to the update step of the Kalman filter, and then you perform your filter update. And in this case, when you do the filter update, the whole matrix will be modified. So you modify the full state, and you modify the full covariance matrix. So in principle, I'm not sure if you can see it completely here. Since this pose is correlated to this pose through the motion, and this landmark is correlated to this pose through the prediction. Once we update this landmark here, it gets smaller, but we also get this one smaller, and we also get the one previously smaller. Okay? Because all this correlation, they just propagate a correction back into the chain of transformations. Okay? If here and here we will all have zeros, this will not happen. So if in this case we have a full zero here and a full zero here, when we do the update, the only thing that changes is this part of the state space, but we will not get any reduction in uncertainty in the poses. Okay? The reason why we get this reduction is because there is correlation, spatial and temporal correlation among the states. Yes?
When would that be the case, that there are only zeros?
That's almost never the case, but you can imagine that, for instance, if you're staying still and you're certain about your pose, okay, and you observe a lot of landmarks around, and then you only observe one, then the other will be independent to that one, because there is no uncertainty in yourself. If then you observe something and you correct yourself, then you will also correct some uncertainty there. So in most of the cases, if there is some transformation, there's always some correlation. Other things like somehow can be independent is, for instance, if you have a set of pure GPS coordinates. No, these are all can be independent, but then you also imagine that maybe you have different robots. Now, different robots, each of them has its own sensor. They never see each other, so you cannot play that. But as soon as they see once, then everything gets correlated back. Okay, does it answer your question? Okay, so now let's think about something very concrete and the simplest case. We have a robot in the 2D plane, so x, y, theta. We have a velocity-based motion model, so we know the translational and rotational velocity of the robot. We assume that the robot observes some point landmarks, so it's just x and y in the environment. And we also assume that we know exactly which landmark we are observing at each time step. We have a range-bearing sensor, so this defines our sensor model. This defines our motion model. These two defines our map structure. And as I said, we have known the association, and we also have a known number of landmarks. So in this case, we do not need to increase the dimensionality of the state space because we know from the beginning where the landmarks are. Okay? So, yes?
It's not only know the number of the landmarks, also know the exact location of the landmarks.
We don't know it at the beginning, we observe it, so we are trying to estimate. We just know that there are 10 landmarks. Okay. No? That's the only thing that we know. In principle, you can think of, you know that there are an infinite number of landmarks, no? And you just do not know at all where they are. And whenever you observe one that you have not observed before, you update the next one. So you can think of there is more than what you need, and you're only interested in the part that you see. Okay? Now, the first thing we need to do is we need to initialize the filter. So we assume that the robot starts in its own reference frame. So the robot is at 0, 0, 0, and is completely certain about that. So that's an assumption that we put in the system. This means that the initial position of the state, so the initial min, will be the 3, 0, 0, 0 of the robot, okay? With the uncertainty, that's the block we are interested, as 0, 0, 0, okay? So it's a completely zero uncertainty. It means we are sure where the robot is. And then we have no idea about where the landmarks are, so what we do is we just put a theoretically infinite covariance matrix on the diagonal of the landmark. So we say, I have completely no uncertainty, no knowledge of where the landmarks are, and we just put a 0 number as the mean. This will not make any difference whichever you put here, as long here is infinity. If you put a different numbers and there is not infinity, then it will make a difference. But that's just like a theoretical initialization. I know everything about the pose, and I know it's in 0, 0, 0. No uncertainty. I know nothing about the landmarks. I put by default in 0, 0, 0, but I put an infinite covariance there. And we also do not know anything about how they correlate with the pose. That's why we put 0 and 0 up here. So we assume everything is independent and they're just there everywhere in the world. Okay? So this doesn't define a proper distribution, but you can imagine, like, in the limit how it will work. Okay? Then the first thing we need to do is we need to predict the state of the system. So we have our motion model, our prediction function g, and for now we haven't specified it yet, but we know it's an odometry, it's a motion, it's a velocity model from the odometry, no? And then we need to predict our covariance. So let's see now how g looks like. So I'm going to do something slightly different than what's in the book, but I will show you then also how it's presented in the book. They're actually the same thing, it's just a bit different how you reach the goal. So one thing is this. Imagine this is the motion, okay? So this is our constant, this is our velocity model, no? If you remember it, there is the velocity of the translational velocity, we have the rotational velocity here, and then we have the usual sine and cosine with respect to the angle, so we know where we are, we go in this direction, and then we do a rotation there. So I'm using the simpler version, the one without the final rotation change. But if you want to have the final rotation change, we will just put it here, and if you want to have a different model, you just write down the function as it is, okay? So this basically says, I stay where I am, so I take the position where I was before, and I add the small displacement that I get right now, okay? So this, the question now is how we can map this one to the higher dimensional space, no? Because we have, as you have seen before, we have something like mu bar equal to mu times t. Let's get on the same, yes, okay, t minus 1, okay. And this actually is a function g of mu t minus 1 and ut, right? But now you've seen that this function is actually just on x, y, theta, no? So we need to find a way of projecting everything up there. So how do you think we can do that? So this would be something like, imagine you have x, y, theta, and then we have, this would be x prime, theta prime, this is what we have, equal, and now we have x, y, theta, plus, and let's say this is our g, no? That's what's written in here. But we also have m1x, m1y, mmx, mny, no? So this will just cover one part of the update, and the question is, how do we cover the other part? Any idea? Will you do, we'll just put them as they were before? Will you change them? So the robot is moving. Hmm? Exactly. So then they will just be the same as before, m1x, m1y, the same mnx, mny. That's our nice vector. And our now function will be then g for here and a nice 0 in there. Okay? So that's our function will look like. So you can see it more compactly by saying this is equal to the identity times mu at t minus 1 plus g of the one we've seen before and 0. No? So that's how we do the whole compact way. This will be an identity matrix, which is the whole dimension of the state space. And here we say that 0 and the rest, and just the part that you're interested in there. Okay? That's how we can write it compactly. And that's one way of doing it. The other way, and that's what the book does, it's slightly different. So they basically use this f here, which is something that brings a low-dimensional vector into a high-dimensional space. Okay? That does basically the same thing as we've seen here. I'll probably do it on the side, because that's what we want to have, no? And if you look at what the book does, it's something like I have mu t is equal to mu at t minus 1. F is made by, there is an identity here, and there is a lot of zeros on there, okay? And then it transposes it. So basically, it's a matrix which is equal to an identity up here and zeros up here, okay? So that's how this matrix looks like. Because we have that F is equal to I, 0, and then it takes F transpose up here. So we just flip it. And there is just our nice G here. And if you multiply this together, you get the mu at t minus 1 plus this times this is G, and this times this is 0. Well, it's exactly the same thing, but just using this intermediate matrix to get up there. Okay, so that's exactly the same function. I just think it's easier to remove the f because you have less multiplication, and if you know the structure, you can just use the structure. But it's good to have the parallel on what's written in the book. Is it all clear? Any question? Okay. Yes.
And I think the dimension of the rightmost matrix should be n times 1, right? It's only 3 times 1.
That's what we've seen here, no? G is this one, you mean?
Yes.
This one is 3 times 1, okay? So it's 3 rows and 1 column, okay? Now, when you multiply by this, which is, so this is just for writing it nicely on the whiteboard. This is actually a matrix that goes like this. So that it's 1, 1, 1, 0, and then 0, 0, 0, 0, 0, 0. It's just, it's compactly written like this, and we put the transpose to move it, no? So when you multiply this with this, you end up with something like that, no? That here is this matrix transpose. You multiply by this, which is a 3 by 1, which is exactly this matrix here, and you end up in a matrix which is the full state space times 1. Okay?
Well, if you say, and if you extend the zeros for the fx transpose, then, but the rightmost matrix still remains the same dimension, so they cannot do the multiplication because it is
Okay, so let's do like this, no? Okay, let's do it step by step. So the dimensions of G is, so G belongs to a matrix which is 3 rows times 1 column, right? Okay. Now we have F. F is equal to this one, E and 0. So it belongs to R. It has 3 rows, and let's say it has big N column, okay? Where big N is the number of elements in the state vector.
Okay.
Now we get F transpose, which is in N times 3, and we get F transpose times G, which is in N times 3 times 3 times 1. It's R N times 1. Is it clear? So probably the confusion is because F is actually transposed. So you see it written like this, but there's a transpose there that changes the order of the dimension. Okay? Any further question? Okay. So that's where we get here. And this is how we do the prediction, basically. So we just apply the function to the previous mean, considering the input that we have. As simple as this. Now we need to do the prediction of the covariance. And here we know from the EKF that we cannot use the function directly, but we need to get the first order approximation of the function, which is a Jacobian of G with respect to the full state space. Okay? So G is again what we've seen there. And we can see now, if you look at G, G has somehow this structure, okay? The Jacobian. Because if this is our function here, we know that the Jacobian with respect to everything but not the motion is just an identity function, okay? Because the map does not change. And therefore, we have the identity down here. If we do then the Jacobian with respect to the other components, so the robot pose, then we have something that depends on G. Okay? Is it clear? So how do we compute the Jacobian? That's simple differentiation using chain rules. We need to get this function. This is the one, our custom, our velocity motion model. We take the derivative with respect to x, y, and theta. And basically, when we do this, we get there is an identity because we have this part which is actually the same as before. And then we have the derivative of the internal part. Okay? So we take the partial derivative with respect to 3 different variables and we stack them again on a vector. And we will end up in something like this. Now, this is the partial derivative of this function with respect to x. There is no x, so it's 0. This is the partial derivative of this function with respect to y. Since there is no y in here, it's 0. And then we take the derivative with respect to theta. So the sine becomes the cosine, and the sine here again becomes the cosine, and here we just leave the thing inside. It should be multiplied by the derivative of this. Theta is just as a single element, so the derivative is 1. We multiply by 1, and that's how we get this. The same thing for here. Derivative of cosine is minus sine, and so on. Okay? And for theta, we know that the last one is does not depend on x, y, and theta, so it's just a full line of zeros. Okay? So our Jacobian will then be the identity plus this. So basically I will be this matrix with 1 on the diagonal. Okay? And that's what we obtain. Any question? No? Okay. So, and that's basically it. So this is how we do the update. We take this G that we just seen, multiplied by sigma, multiplied by G again. We add the RT, and the structure is something like this. This is the structure we have seen before. This is a structure of the matrix. So the part that only interests the robot pose, the part that only interests the map, and the cross correlations. We multiply again by this, which is transpose. The transpose of the identity is the same, but we just have to take the transpose of G. And then we add our nice noise terms on the motion. We'll see now how this actually looks like. If you look at then what happened in the full covariance matrix, you will see what I've shown you before with the colors. No? The only thing that actually changed is this part up here, because the robot moves, and the correlation of the new pose with respect to the map. But the uncertainty of the map itself does not change. Okay? That comes automatically from the fact that the function that updates the state over time does not touch the map part. Okay? That's because we have this nice identity down here. Okay? And this identity comes because our nice function here has an identity part, which is this, and then it has a zero part from the update. And when you take the derivative of this, we'll just get an identity there, because the zero will be a zero. So the same thing that we've done here, no? You've seen that there is a similar part plus a function, and the derivative is the identity plus the derivative of that. And it will be the same if you look at the bigger picture, where you have an identity here, and then this part will just be a zero added there. Yes?
To get from the second line to the third, you get from a vector to a 3 times 3 matrix because of the differentiation of through 3 variables.
Exactly. Okay. Yeah, so that's what's called a Jacobian matrix. No? It's like a matrix of partial derivative. We have 3 functions that define the 3 lines, the 3 rows of the matrix, and we have 3 variables that define the 3 columns. Okay, so that's where we are. That's the update, and that's done for the update part. One thing we just left in unknown is this R, and we can see how this comes, and you can see here again the same with this F matrix as is done in the book. The idea again is that this matrix will just bring everything up. We have seen how it works with respect to the update of the motion, that it's the same when we multiply this by G. And the same thing happens if we want to do then with the covariance. So we can just write it all together by just saying that's the identity plus F transpose, this part, which is the Jacobian of G, times F. Okay? But when we do this multiplication, what will happen is that we have exactly this matrix here. Okay? Because what we do, I can actually do on the whiteboard, it's easier. Can I delete this part? So we have F, which is done like this as well. So we will have identity and 0. Then we multiply by our G of x, I think we call it before, GT of x. And then we multiply by F again. Okay? If we just do this, and this is the usual 3 by 3, this is 3 by 3, this is n by 3, and so on. The same thing that happened, it's the same F that we have seen before. We just multiply them, and we end up, we just multiply this by this. So we have identity times 0 multiply by GTX 0. We multiply this, and we get this structure here. GTX 0, 0, and 0. Okay? So that's what we see. So basically, the effect of this F is to take G from a lower dimensional space and bring it up in the higher dimensional space, and leaving everything that is not touched to 0. Okay? So basically, it's something like this. If we see it in 1D, I'll probably then delete this part here. If we go on the 1D to 2D, now imagine G is something which is in one dimension, okay? So it tells you I have a point here, okay? And that's my one-dimensional space. Now I increase another dimension, and I have my f in this way, which is 0 on all the dimensions besides the one I'm interested. The point will still be here. So I will not change the position of the point in the space, but will just extend the missing part with zeros. That's what it does. And it does it for every operation. So if you have a function that is only defined in here, we again define it in there and extend the part which is outside to zeros. And the same if you do a second order, so covariance and so on. So that's the idea of f. And again, you can see they will update in this way, where you have f bringing everything up, or you can see the update in this way. Okay? Where you know the structure and you just write the structure there. There are two different ways. I like this more because it's more compact. You seem there's less clutter on what's happening there. But mathematically are equivalent. And that's actually the way it's written in the book. So I'm putting it for reference. For RT, it's the same. You can either imagine, so RT is a matrix which just depends on the motion. It's a 3x3 covariance matrix. But you can imagine that you can do the same trick. You can project it up using F. Or since you know that this is going to have a structure like this, you just have a matrix already like this, where it's RT here and all zeros there. Okay? So, and that's again done. We can do a few minutes break, and then I go on the correction if you want, or I can go on and stop before. What do you prefer? Break, non-break? So one break. How many for break? 2. How many for non-break? 2. Okay, so it's 6 people, 2 for break, 2 for non, and 2 don't care. What about you guys? Okay. No break? Is it fine if I go on? Or you just finish 15 minutes? Or let's do something in between. We do a half break, like 7 minutes break, okay? Welcome to, okay, so half break, gone. We can finish it. So right now we just went to the prediction step, and what's missing is the update and measurement correction step. Again, these are the usual formula of the Kalman filter, and what we are focusing right now is what's the structure of this H, which is our measurement matrix, and also which is our H, small h, which is our measurement function. Okay? And we'll also take care of what happens if I'm observing a landmark for the first time and how do I handle that. Okay? So, one thing we are considering is we have known data association. So basically it means that we know these variables, which says the landmark association of observation I at times t is landmark j. Now, that's just a way of formally write data association variables. But in principle, this just means that I get a number from my sensor, and I know that this number relates to landmark j in my map. Okay? And this number will be defined by which kind of sensor model we are using. Now, if it's bearing only, will be the angle. If it's distance only, will be the distance. If it's bearing and distance, then you have both of them, right? So what we need to do is to take care of initializing the landmark if it's not observed, okay? And then, after that, we need to take care of computing the expected measurements, compute the Jacobian of our measurement function, will be this big H matrix, and then we go on with the Kalman game, because we have all the components that are needed for that. So, yes?
Here, the first step, I initialize the landmark unobserved, means the in a matrix the location of the unobserved lemma is 0, right?
Yeah, it means that I've not observed this landmark so far, no? Then it means in the matrix we still have the 0 mean and the infinity covariance, no? So like this, like unobserved state means I don't know anything about that, 0 mean, infinite covariance. Okay, so first thing first, we get, as I said before, range-bearing observations. Range-bearing means our z, so our abstract variable for the measurement, is composed by these two concrete elements. One is the range, so that tells you how far away from me is the landmark I'm observing. And the other one is the bearing, so the angle. It tells you in which angle I'm observing it, okay? So for instance, you can say it's 3 meters, 40 degrees, or something like that. What we do is, if we have not observed the landmark so far, we need to transform it with respect to the reference frame, okay? And in general, this is actually the relation that we have with respect to the pose of the landmark in word reference frame or the map reference frame, considering the pose of the robot in this reference frame and the relative measurement that we have. Okay, so basically you can already imagine that somehow in this way we will have, so this also considers our measurement function. Our measurement function will be the other way around, you know? So we want to know how to get these angles and this range, given that we have the location of the landmark and the location of the robot. But this is just the relation, and this is just, I get a positions in x, y relative to the robot by just taking the cosine and the sine of the measurements that I get, no? Because I know the robot is rotated in a certain way, is observing with another angle in this one, and it means that this is the relative angle between how the robot is facing and the landmark. We take the sinus and cosinus to get the x and y coordinate, and then we put them back in the position of the robot, okay? So we have it relative to the robot, and then we move them back relative to the word. And this is the connection between word and robot, no? We don't do the matrix transformation because it's already included in here, no? The fact that we are rotating the relative measurement is because we are just considering the rotating angle. So we don't need to care about the final orientation of the landmark because we'll just be in x and y, okay? Now, if you want to initialize a landmark, this is what we will put in the initialization phase. Now we'll just say the mean of the landmark will be this one, okay, in our matrix. And for covariance matrix, we still leave the infinity there, so we don't touch it. And we do it because in this way we can see how we'll see that how the full update of the Kalman filter will take care of the real update of the covariance matrix in this case. Ideally, you can skip that. So in principle, you can also skip that, and you will just need to compute on your own the correlation with respect to the robot pose and the final marginal covariance there. But if you just leave it as a pre-step and then you let the whole filter doing this, you will get exactly the same thing. So it's just easy to implement. You don't have two phases, initialization, none. You just have one small thing to do. If you have to initialize, we just put the mean to this value, okay? So if you want to then get the expected observation, as I said, we need to invert what we've seen before. So we first take the difference between the landmarks x and y, this is the part which is in the predicted state, and the robot pose x and y. Again, it's the part which is in our predicted state. And this will give us this delta here, and as we have seen before, this delta will be just this part here. No? We get this, and we know that there is a range, and there is cosine and sine. Now, to take the range, we can exploit the fact that if you take the square of the delta and take the square root of that, this basically exploits the fact that cosine and sine square, they just sum up to 1. So we will have r squared that multiplies cosine square and sine squares, and they all sum up to 1. So we can probably write it down here for simplicity. But our nice delta is something which is r multiplied, so let's write it full thing there, r ti multiplied by the cosinus of our angle measurement, phi ti, plus our mu theta and t, so it's written the same way, and the other one will be rti times sine of our angle ti plus, okay, so this is our delta vector, no? So we need to get r out of this, and we need to get phi out of this. And r, you can see that if you take, this you can imagine that you just need to care about the distance, no? So it will be like the length of this vector. And you can also see if you take now this vector multiplied by itself, like it's been done here, you will end up with something that delta transpose delta is equal to r ti square cosinus square, and it will be the same thing here, plus rti square sinus square. No? The same thing here. If you collect the r, you end up with something which is rti square cosine square plus sine square. We know that this one is equal to 1. Okay? So we know now that this guy altogether is equal to rit square. No? So we just take the square root of this and we get the r. Okay? Now the difference now is, the other complicated thing is how to get the angle. If you reason about the same thing, basically you will say that once you take the r, and in principle you divide one of the two coordinates by that, you can take the, can either use the arc cosine or the arc sine. The problem is that they're not stable, so we all use the arcotangent, and we use what's called arcotangent 2. Okay, and that's because this is a very function defined all over the circle, while sine and cosine, they have singularity when one of them goes to 0, no, they get to infinity and so on. So anyway, to make things easier, you need to consider if you divide everything by sine, you will have that here, for instance, you will have maybe 1, and here you will have the tangent, and then you can take the arcotangent of that. And you put the y coordinate, so will be then this value here will be here, and you put the x coordinate there, and you just take the angle between them. This will give you the absolute angle with respect to the world frame, and to this one you need to subtract the angle of the robot, no? Because it will give you what's in here, the part which is here inside, no? And then you subtract again the angle of the robot. Okay? Does it make sense? And this is exactly our AH function, no? That's how our function depends on mu of t, okay? There is a dependence on x and y from computing the delta, and there's a dependence on theta by computing the difference in there. This is now one, that's the function. Now we need to consider how to compute the Jacobian of that, no? And again, we do the usual partial derivative idea, and in this case we have also that this Jacobian is a low-dimensional one, okay? So this means that our function actually only depends on 5 variables of the state space. It depends on the pose of the robot, so x, y, and theta, but also depends on the x and y of the landmark that we are considering, okay? So for now, let's just focus on the Jacobian of this restricted space, and then we can see the usual trick to bring it up in the higher space. So this again is the derivative of the square root of q with respect to x, y, and all the other variables, as we've seen before. And if we go and expand them, we'll say that if we do the usual chain rule, we'll see that this one with respect to x is equal to, we first do the square root, then we apply the chain rule, and it ends up with 1 over q minus square root of q times delta x, no? Where delta x is this value up there. Is it clear? That's just applying the different chain rules. So first apply the q, and then since we know the q is this times that, we only consider the x, this is the square of x, and that's how we get in this formula here. No? So here is derivative of square root of q, you end up with that, times this, minus 1. No? It's just one step after each other. Square root, the square is 2 delta x, and then inside there is a minus, becomes minus 1. Okay, question? If you do then the whole process with the chain rule with all the components, we end up with x and y being roughly the same, as you can see here. So with respect, the first part with respect to x and y, it's basically almost the same. It's just the difference in which part of the delta you take into account. With respect to theta, it's 0. There is nothing in the range that depends on the angle. And with respect to the coordinates of the x and y of the landmark, is the same as the x and y of the robot, just with a different sign. Because as you can see, they are entering the function in the same way. If you look at the second level, then you will have that this is equal to just the part on delta y, and here is the part minus delta x. And this comes again from the derivative of the Autonome, and then different simplification of the chain rule. If you want, you can try to do it at home and be sure that it gets exactly that. Okay? Then, with respect to the theta variable, we just have this part here, so that's why there is just q in there, and so on. Okay? So this is just the form of the Jacobian. But this one is a 5-dimensional, so 2 times 5. And we have, again, our state space, which is a higher dimension, because there's also all the other landmarks that we are not observing right now. How we go up there? There are, again, 2 ways. One is we can do it as the book was doing it. So we can see that there is our low-dimensional h, and then we have our f that takes the high-dimensional space and projects it down there. Okay? So this f now has a different structure as the one before, and has a structure which is made like this. So it's we have on the left, so the number of rows is the number of elements that are in H, so it's the number of variables that we are carrying. So our f now is done by, we have a part that depends on the robot pose, identity here, and then for the rest of the variable is 0, because we know that they do not depend there. And then there are a lot of zeros until we reach the landmark that actually is the one observed. And for the landmark which is observed, we have a 0 in the upper part, because we don't touch the robot pose part. And we have an identity down here. Okay, so basically say select this guy and put it in this line of variables. And then again we have a part with all zeros. Okay, so that's how our matrix looks like. And that's exactly how it's been shown there. Now, if you multiply this with h on the left, you end up in a very particular or typical structure of this H matrix, which basically it's like this. You have, so if you've seen before, that's our H. So you will have the usual structure here, 1 over Q minus q and delta x minus square root of q and delta y. Then you will have 0, and that's somehow what depends on the robot pose, and you have delta y, then you have minus delta x, and then you will have minus q. And then, basically, this will just be expanded and elated with a lot of zeros in the landmarks that we don't care. So then there will be a lot of zeros here. Then you will have the part of the landmark that you care, so there will be plus square root of q delta x, square root of q delta y, then we have minus delta y and delta x, and then we will have a lot of zeros towards the end. Okay? So that's how our H matrix will look like. So again, if you do the parallel, you can write it compactly in this way, which is the low-dimensional H. You can write it as a part which depends on the robot state and a part which depends on the landmark. Okay? So that's how you can write it down here. Basically, this is this block here, and the other part is this block here. Okay? So the full high matrix is then something that looks like Hx, zeros, HL, zeros. Okay? So that's how you write it more compactly. And the effect of this F, so as it's also written in the book, is exactly the one of taking this small h and bringing up to this form. And we can see it by just doing the multiplication. Our F is something like identity 0, 0, 0. Then we have 0 identity and then 0, 0. We take this, we multiply on the, is actually on the left. So we take this one on top, which is Hx, HL. We multiply it by that matrix, which is 1, 0, 0, 0, 0, I, 0, 0. And this is just, you take row by columns, and this is, the first row is Hx, the second one is 0, and you do for all the zeros, and then you get HL, and then you get all the zeros, no? Which is exactly what is done up there. So again, you can think of it by having a selector matrix that gets the right variable out of your state and a function which only cares them, or you can put the selector and the function together in something like that. This is something more compact to write. This is a bit more extended, but you have the two aspects separately, no? Okay? Any questions so far? Okay. So once the h has been computed, the function, we know the function, we know the Jacobian of this function, so we know how to approximate it. We can just get back to the Kalman filter, we compute the Kalman gain, we have all the components that we need for the Kalman gain. We have the predicted sigma, we have the Jacobian we just computed, we have our Q that comes from our sensor. In this case, we do not have to expand the Q as we did before with R, because the H is the one that takes the full size covariance matrix and just takes the part which relates to the current observation. Okay? So therefore, we do not need to expand the Q as we did for the prediction step. Okay? Then we have everything for the rest. We have, let's, without the slash is better, the mean, we know how to compute this function, we just have seen before. There's just a difference, so this we get, we take the difference. The Kalman gain has been just computed, we can get our new mean, we can get our new covariance. So then it's again the same as any other extended Kalman filter algorithm. And then we return the two means, okay? We do it, and the filter is done. Any question? Is there something missing? No?
Can you explain again about this expected observation and the observation? So during the algorithm, during the calculus, we use a ZTS. And you said from the range bearing observation, that's the ZT we get is the true observation, not the expected observation.
So we have a model, a sensor that gives us something, okay? Our sensor, let's get back from the beginning here. Okay, so our sensor gives us this, okay? Tells us how far is something from us and in which direction it is. That's what our sensor does. And we know how to relate this information with respect to the world, okay? So here is the mean of where we think it is in our belief, okay? And that's how it's supposed to be, let's say, if we project everything down. But in principle, what's happening is that given this, no, we would like to be able to obtain these values. And that's what we're trying to do, okay? Because we need to have something that has this form. So when we do the update, when we compare the observation with the predicted observation, the only thing that we have for sure is our sensor gives me these numbers. And now I need to find a way of computing these numbers from my state space. In case of range bearing, which is this one, I need to find a way of getting the range, and I need to find a way to get the bearing. And that's how we do it. No, you can see it also visually. This probably. So what I have is, this is my word frame, okay? Then here is my robot, okay? And I think that here is my landmark, okay? So this is what I have in my state. Now I know that the robot does something like this, no? It needs an R, okay? And it needs a phi, that's the sensor. So now I need to compute this angle, and I need to compute this distance. That's what my sensor gives to me. And I need to compute this considering all the things I know, which is just this guy, and this angle. That's what I know. Okay, that's it. And we take now the distance by getting the difference and the of this vector here. And then the angle is, we take this full angle and we remove this guy. That's what we do. Okay, so what's actually missing from here is, I haven't told you how to do exactly the initialization of the unknown or unseen landmark, did I? Yeah, so that's how we do it. So now you can see a bit expanded of everything in here, is that we can have actually multiple features to observe at every time, so we need to consider all of them together in the update. You can do two things. You can consider them independently, or you can consider them all at once. In principle, it doesn't make much of a difference if the measurements are actually independent. It does if they're not, and it also does if you do if you don't have known data associations. Then you might have problems because you will maybe discard some landmark if you already incorporate others. No? Like if you have to choose this observation is associated with this landmark, it's different if you do it without knowing anything or if you already start getting some measurement in there. Okay? But in this case, let's get the simplest one. They are independent, we know the association, we just have to loop all over them. And we integrate it one at a time. We get our label, so we know the association in this case. If we know that we have never seen it, so we need to keep track of the landmark that we have observed so far, we just put this, which is the predicted position. So let's say we just assume that the only thing I can trust is my sensor. So the landmark is exactly there. Okay? Now you can also, you might in principle skip this part because by having the infinite covariance, this should come automatically. The problem is that since you will never put an infinite covariance there, because you need to put some numbers on the computer to make it working, this makes it work better, because you will really have it exactly at the location where it's observed for the first time. If you don't do it, numerically you will merge and fuse two measurements, one that tells you very uncertain but I've seen it at 0, and the other one more certain but I've seen it there. Okay? So that's the reason why we insert this part in there. Clear? Roughly? Okay. Then we do the computation of our H function. We do our Jacobians, we do the trick with the F, or we just do the exact composition of the H. In this case, this H here will then be the expanded one, but that's the difference. So you can see it here multiplied by F. If you already have it with the zeros at the right place, you don't have to multiply, but you end up in the same matrix. And that's the end of the algorithm. Okay, so some kind of tricks for implementing it. You can do one full step for all of them. So basically you can stack all the observations into one vector. Then it means that you will get a lot of stacked vector in here. It means that your H will then be a lot of different H's. Okay, so this will then be, that's the first landmark, second landmark, maybe it's here. No? So there will be just this H at different places. Or if you want to go for the F thing, you need to make a very big F which selects everything. But in principle, you do the update in a single step, because you can exploit the fact that matrix multiplication is fast. You can parallelize it quite nicely. There is only one update step. You don't have to do this for loop and take all the different update steps. So it's just easier. One thing you have to be careful is about angles. Angles are nasty because they are not Euclidean, so they live on a manifold, and you need to be sure that, let's say, 0 and 360 degrees are actually the same angle. Although if you just take the difference, is a huge difference. It's like the maximum you can get from an angular point of view, but actually it's not true. No? So you have to be careful on that. And as I said, you don't need to create the F. No? So you can just, if you know the structure of these matrices, you can just use as it is. You don't need to do any F. And if you do things in Octave, MATLAB, or any language that allows you to use sparse matrices, you don't even need to allocate a lot of memory. You will just say, this matrix is sparse, it's zeros everywhere besides this part and this part. And this will save you a lot of computations when you use these tricks. Okay? So that's it for the Kalman filter. Before leaving, I give you just few things on small different quirks and perks on what happened in reality. So in reality, we do not know data association. So there is a problem called loop closing, or basically just, you can imagine this is just hard data association. Okay? The difference between the normal data association and the loop closing is that normally the uncertainty is harder in this, so that the simple nearest neighbor heuristic, just take the one which is close by, might not work. Okay? So that's the reason why some people name it differently and they consider it as a different problem. But in principle is that you need to recognize a place where you have already been before, and you want to associate your measurement with the landmarks, and you have normally high ambiguity, so that two things, one measurement can be associated to multiple landmarks. And you can also have symmetries, so actually you cannot even sometimes consider geometric relations between them, because there might be very similar structures, so you need to reason about that on a higher level. But the interesting thing is that once you do a correct data association, or actually once you do any data association, correct or not, the uncertainties will just collapse. So you really get very certain about your map in a lot of places by just observing something far away. The reason is this. Imagine your robot starts here, goes around this loop, and then comes back to the original place, okay? So when you are able to associate something from here to there, you see that there is a lot of certainty on where this landmark is, and if you do then the update, what will end up is something like this. You will be very sure at the loop, and then we'll just propagate this certainty back on this chain here. And you can imagine that before closing the loop, the uncertainty gets just propagated in one direction. That's why it gets higher and higher. Once you close the loop, you have two uncertainty chains through the correlation of the motion of the robot. One, it goes in this direction, and one is the backwards propagation that you get by just measuring the landmark there. And they will somehow merge here in between, and here somehow they will merge the two estimates together. So that's just very high level insight, but that's what you can imagine here. That's why before the more uncertain place was this one, and now the more uncertain place is the one somewhere in between the two places. Okay? And that's one important thing. Another interesting thing is that you can reduce the uncertainty and landmark, and you can actually plan for this kind of event if you do some active navigation, active exploration of the environment. So the problem is that since this will happen anyway, regardless of if the data association is correct or not, you might end up in very bad estimate of the environment if the data association are wrong. Okay? The reason is that the whole estimation framework assumes that the measurements are correct, and the only thing that they take care of is reducing the uncertainty. So using the uncertain notion of this to get some better estimate. But if what I'm telling you is completely wrong, then you will end up in a wrong estimate. And let's say wrong measurements, in principle, should be measurements that brings you no information at all. No? But since the notion of being correct or wrong is something more higher level, you need to be careful on that. And that's one of the big problems also of what's called loop closing, because if you do it once wrong and you commit on that, then you will have problem in the future. So it might be that your map is not usable. So you need to be careful on this. The other interesting aspect of the AKF is that in principle and theoretically, everything gets correlated with everything else. That will happen with certainty and will happen eventually. No? And the reason is that there is, every time that you measure something and you get some connection back, you will just propagate all of this. And that's because the robot is moving around. So the fact that the robot moves attaches correlation to the different poses of the robot. The fact that it's observing something, it means there is always like a chain of measurements, direct or indirect, that connects every pose of the robot, every landmark with the rest of the world. Okay? Some of them might be really thin, like the one down here, and some of them might be really strong. Okay? So most of the time you might consider to neglect them. So sometimes you can neglect them, and we'll see next week how you can actually deal with neglecting some of these correlations, what happens. But if you don't, you will just get everything correlated. And if you imagine a situation like this, where I haven't observed anything, but I just have a prior of where the landmarks can be, this is my covariance matrix or correlation matrix. I have the poses a bit correlated up here with one landmark, and this other one you can imagine are either the infinity value that we put in the initialization, or someone tells you a rough idea where the landmarks are, no? That you can imagine as a prior knowledge. The more you go around, the more these things get correlated. So the darker elements means stronger correlation, lighter elements means lighter correlation. And you can see also a pattern of bright, dark, bright, dark, bright, dark. That's basically saying that x coordinates correlate strongly with other x coordinates, and y coordinates correlate strongly with other y coordinates, but they do not correlate much with each other. No? That's just an intuitive way of saying if I have an object and I move it on the left, everything on the object moves on the left, but I don't touch anything on the up backwards, on the y direction, and the same here. No? Since everything is connected, everything is correlated, but you anyway still keep somehow independence between x and y. The fact that they are not completely zero is because sometimes rotations correlates x and y, but doesn't correlate it that strongly as it will be a x with an x. No? Okay, so that's the reason of this kind of checkboard pattern in there, and the theta here somehow decorrelates almost everything, because it's, in this example, it was a very linear sensor with respect to theta, so there's no connection between them. But in general, it can also correlate the rest of the map. Okay, so that's an idea on this. And if you go on and go on, you will just get everything super correlated. The interesting thing is that correlations is not bad, because actually it's the only way to get a correction from one part of the state space being propagated to the rest of the state space. You cannot ignore it, and you do not want to ignore it. But sometimes, because either you get sometimes estimates which are too optimistic, so you think that something, you think you're more certain than what you actually are, or also you will not propagate back information when you do the update. So it's just something that you don't want to ignore, and it actually helps you. In some cases, you might think about ignoring it for efficiency, but then you need to be sure that you know that you're dealing with something which is not exactly the estimation that you're doing. So you are approximating something instead of getting the real values out of it. Another thing is that once we compute the estimate of the individual landmarks, so you can see, like for instance in this case, they always start as the uncertainty of a landmark will be the same as the uncertainty of the robot pose where it's been observed the first time. No? And that's because you have no other information about that. The only thing that you have is the transformation from the center of the world where the robot is, with this uncertainty, plus the uncertainty of the measurement. No? That's why when you start with very far away, you get some very uncertain landmark. Now, every time you go around and you go around, actually you can reduce this uncertainty by each time you reobserve this landmark, or sometimes by observing something close by and so on. But one thing which is interesting is that this uncertainty always decreases. So there will never be an increase in the uncertainty of the landmarks. And that's because the only way in a Kalman filter or a bias filter to increase uncertainty is through the injection of uncertainty through the motion model, through the propagation to the prediction step. And since the prediction step doesn't touch the landmarks, there will never be an injection of uncertainty in there. But there will just be a monotonic decrease of uncertainty, because that's what happens during the correction step. You can see it from the formulas. It was always like identity minus something. Okay? There was never a plus. But the only plus was in the prediction step, where you said covariance equal something plus R. No? And you can imagine plus means adding noise, minus means removing noise. No? The other interesting aspect is that in the limit, the covariance of the landmarks cannot be better than the covariance of the robot. Okay? So this means not the covariance of the robot at the time where it's been observed, but the covariance of the robot at that position, even after the correction step. Okay? So what it means here is that imagine that you initialize your system with this uncertainty. So the first pose of the robot is this uncertainty, You can never be better than that, okay? And everything at each time that's connected in the future or is connected to the landmark can never be better than that. Now, this will be like your lower bound. Since you assume normal initialization that you have zero uncertainty of the initial robot pose, then this means that you can still bring all the estimate of all the landmarks eventually to zero if they are observed from the first pose, so if there is a direct observation in there. But what can happen is that you can never be better than the pose itself. So the idea is something like this. If you have a pose here, no, and the landmark here, if you shrink this down here, you will also shrink this down here. No? But since there is this connection, whenever you manage to shrink it more than that, the connection will shrink this pose as well. So they are kind of connected together. No? That's somehow what this this slide tells you. No? This is kind of insight on what happens in the Kalman filter. Okay? And to end up, I'll just show you a few real-world application in reality of the extended Kalman filter. This is a vehicle in Sydney. This is the park in front of the University of Sydney. It mounts a laser scanner here, and what they do is that they have a simple detector that tells you if I'm observing a tree trunk. No, it just looks at, is there something that looks like a circle? Yes, no, that's a tree trunk. And they also have in the state of the map a signature for tree trunks, which is the size of these trunks, no? How large it is. And this helps to distinguish which landmark to associate with which observation. What they have is, this is how they drive around, so that's how they collect the data. It's kind of old, it's probably, I don't know, 15 years old from now, something like that. And the robot is moving around, it's measuring these trees around there. This is how the, let's say, map look like. The red is the path of the robot. These blue crosses are landmarks that has been observed and estimated. These other colors are somehow spurious measurements, so there's a lot of engineering and algorithmic things to understand if a landmark is just a good one, is a bad one, has been already validated to say, I'm sure that's something that's a real trunk and it's not a wrong measurement that I got, or like a person walking by or something like that. No, so you need to be careful on what you put in your map. But anyway, the blue are the good one, and the other one are different stages of idea, of let's say, validity of being good match for our map. And if you take this and you put it on the aerial images, you will see this is the path of the robot, and each of these dots is one of the trees. The path and the image are from different times, so some trees have been cut down, some trees have been grown up in the meantime, so it doesn't really match completely everywhere, like here for instance, but it gives a nice idea that the trees, most of the trees are where they're supposed to be, and some others are actually not there yet. Okay? Another experiment that's been done also at MIT, so to get the ground truth, they took like a tennis court, they put these poles at the different corners of the tennis court, so they knew the distance and the relative displacement of all of them, and then they could observe from the laser these poles, and then they could detect them. And here you can see like the odometry run without any filtering, and that's what ends up at the end using the Kalman filter SLAM. No? So you just get, okay, so half break at this nice aligned hurdles on the tennis field. Before finishing up, how costly is this? So the complexity depends on the dimensions of the measurement and also the dimension of your state space. So basically when you do your update and when you do all the multiplication, you will always have this big covariance matrix that you need to multiply the rest, no? And this covariance matrix, to have it here, no, has a size of twice the number of landmarks, because it's x and y for each landmark, plus a constant factor for the robot pose. Since it's a matrix, is squared because you need to compute all possible values of this matrix. So you get an n square complexity and also n square consumption because you need to memorize the whole matrix. It's kind of n square values, and you need to multiply each of them every time. No? So when you get very large maps, this becomes intractable because the square here might be too much to be handled if you are a very large environment. For small environments, it's pretty good, works well, and it's actually very efficient. It's very easy to code, few lines of code, and everything is fine. So summarizing, that's like the first solution to SLAM. If everything is linear, you have all nice properties of optimality, convergence, and so on, but it's not the case, so we can just hope that it converges. It does in most of the cases. If you have small uncertainty, small motions, very close observation, and so on, but it's not guaranteed. It can diverge if you have very high nonlinearities and very high uncertainty from your sensors, but if you go on medium, large scale, not really large, let's say more medium scale maps, it works quite well, and it's probably the first thing you will implement, and it's actually also what's been implemented in a lot of real products, because it's easy to implement, algorithmically not complex, it's easy then to debug, to test, to evaluate, and so on. The only thing you have to take care is that the assumptions are actually somehow satisfied in most of the cases, and that's it. There are approximations that reduces the computational complexity, and there are also approximations that makes it better in terms of the nonlinearities. So like how to handle this nonlinear propagation of the error a bit better. That's it. If you want to read it, that's the chapter 10 of the book, Probabilistic Robotics, and yeah, plus some of these parallels of what I said in the book and so on. So that's it. If there is any question, ask, or otherwise we can finish it here. Questions? No? Okay, then see you next week.